Hello, here is our video going over our Chapter 2 Rational Functions test review. Our unit on rational functions covers graphing rational functions, operations with rational functions, inverses of rational functions, graph of reciprocal functions, wholes and asymptotes, as well as limits. Now, as we go through the problems on your test review, do not forget that you need to practice in order to be successful in math. So, here we go. Let's graph some rational functions. Okay, so for letter A, as you can see, I already typed it into my calculator, but let's talk about the different pieces of our rational graph. So it says graph each of the following functions and identify the equations of the asymptotes. So the first thing I want to do is I actually want to identify what my transformations are, because that's going to help me figure out where my asymptotes are. So this right here, I have x minus 2. That means I'm going to be moving to the right 2. And minus 4 means I am going down 4. So normally our asymptotes for the rational functions are the x and y axes, but I'm moving to the right 2 and down 4. So when I move to the right 2, that's going to take my vertical asymptote and move it to the right 2 units. And this crosses at x equals 2, so the equation for my vertical asymptote is x equals 2. For my horizontal asymptote, it's normally the x-axis, but it has now been shifted down 4 units. So I'm going to move down 4, 1, 2, 3, 4, and here is my horizontal asymptote. And that equation is y equals -4. Now, to get the other pieces of my graph, you can graph it into your calculator and look at the table. So if you look on the screen, I already put this function into my graphing calculator, and I'm going to pick the nice points to graph. So I'm going to graph 1, -5, as well as 3, -3. Now, if you'll notice, I picked the points that are surrounding where you see this error. This error right here is one of our asymptotes. So I always want to pick the points that surround the asymptote. So I'm going to plot the point 1, -5. That gives me this piece right here. And I'm also going to plot the point 3, -3. And that gives me this one right here as well. And our rational functions will always extend towards the asymptotes without ever touching or crossing them. So once I have these points plotted, it gives me an idea of where my rational curves are going to be. So there is your graph for 1A. Let's do another one. So 1B, what I notice is I do have this negative. So if I list my transformations, I have a reflection over the x-axis. I also have a vertical stretch of 2, and I am moving to the left 1 and up 3. So let's go ahead and adjust our asymptote. So I'm moving to the left 1, so that shifts my vertical asymptote to the left 1, and that equation is going to be x equals -1. For my horizontal asymptote, normally it's the x-axis, but it has been moved up 3. So I'm going to go ahead and move that up 3. And here is my new horizontal asymptote with the equation y equals 3. Now, I do know that I have a reflection over the x-axis. So normally, when I graph rational functions, they're usually in these two portions next to my asymptotes. But because I have a reflection, what that means is my curves are going to be down here and over here. Now, I do still like to use my graphing calculator and the table to be able to find nice points to graph. So again, if you'll notice in my table, I'm choosing points that surround my asymptote. And I can see my asymptote because there's an error at -1, which just so happens to be where my asymptote was. For this one, I'm actually going to plot 2 points on each side of my asymptote, and that's going to help me because there is a vertical stretch. With that first graph, I only plotted 1 point on each side because there was no vertical stretch, but because this one does have a vertical stretch, I'm going to go ahead and plot 2 points. So I have negative 3, positive 4. 2, 3, 1, 2, 3, 4. So I have this point over here. I also have negative 2, 5, which is right here. And then I have 0, 1, and 1, 2. Okay, so these 2 points, as I connect them and extend towards my asymptotes, they are going to create a much more accurate graph when you have that vertical stretch. So what I would recommend doing is always double checking with that table in your calculator and double checking that your points are matching up with what you see in the table. You can also use the graph feature on your calculator and see that your graph that you're sketching actually matches the graph on your calculator screen. So that takes care of the first topic of graphing rational functions. Now let's move on to operations with rational functions. So operations is when we're adding, subtracting, multiplying, or dividing. So this one is subtraction, and one thing I like to do with subtraction is I'm going to change it to addition right away. I'm going to change this to plus negative 4x. I'm actually going to rewrite my problem so I have more space. And the reason I changed that 4x to a negative 4x is to remind myself, hey, I'm going to have to distribute this negative 4 as I continue with the problem. Now, anytime you're adding or subtracting rational functions, you need to have a common denominator. Usually, in order to find the common denominator, you need to factor, but in this case, we don't really have anything to factor. I'm going to go ahead and put these denominators in parentheses. That way, I know that x plus 4 is one factor, and 2x minus 1 is the other factor. Now, what you're going to do is you are going to multiply each fraction by what the other fraction has for the denominator. So I'm going to multiply my first fraction by 2x minus 1. And of course, whatever I do to the top, I also need to do to the bottom. And then for my second fraction, I'm going to multiply by x plus 4. Now, if you look at my common denominator, I can see that both of them have 2x plus 1 and x plus 4. 2x minus 1 and x plus 4. So now that my denominators are the same, I can go ahead and start to simplify those numerators. And in order to simplify, it's just a lot of distribution and combining like terms. So I'm going to go ahead and distribute this 9 into that first parenthesis. So that gives me 18x minus 9. And I'm also going to distribute negative 4x into my second group. So negative 4x times x is negative 4x squared. Negative 4x times 4 is negative 16x. And all of that is over my common denominator of 2x minus 1 with x plus 4. Now for my numerator, I can combine like terms and rearrange. I'm going to put my negative 4x squared first. 18x minus 16x is 2x. And then finally, minus 9, all over my common denominator, which was 2x minus 1 and x plus 4. And this is your final answer. All right, moving on to multiplication and division. So multiplication and division requires a lot of factoring. I like to call it a factoring frenzy. So you're literally going to factor everything. Now, one thing I noticed right off the bat with my first numerator is I do have this number in front of my x squared. That tells me, hey, I'm going to have to multiply using the box. So I'm going to start by multiplying my first and my last numbers. So 2 times negative 10 is negative 20. I'm going to go ahead and set up my box on the side. And on the top left, I'm going to put my 2x squared. On the bottom right, I'm going to put my negative 10. Now what I am trying to do, and I'm going to do the box diamond method just to organize my thoughts. I need to find two numbers that multiply to negative 20 and add to positive 1. But hey, where did that positive 1 come from? It's right here. So I have plus 1x in the middle. So I'm trying to find two numbers that multiply to negative 20 and add to positive 1. Those two numbers are 5 and negative 4. And that's what I'm going to put in my other spots in the box. So I'm going to do 5x and negative 4x. Now, to continue the factoring with the box, I'm going to look for GCFs in all my rows and columns. So I'm going to go ahead and start with my first column. So I'm starting right here. 2x squared and negative 4x, what I notice they have in common is a 2 and an x. So I'm going to pull out a 2x. For 5x and negative 10, they have a 5 in common. So I'm going to pull out a 5. So it's plus 5. Over here, what I notice these two terms have in common is x. And then for my last row, what I notice they have in common is they're both divisible by 2, but since this negative 4x is negative, I'm going to go ahead and factor out a negative 2. Now, you can always double check your factoring because these two sides right here, when I multiply them, should give me the contents of the box. So when I have x times 2x, that gives me 2x squared. X times 5 is 5x. 2x times negative 2 is negative 4x. And 5 times negative 2 gives you the negative 10. So that's how you know you factored correctly. But I'm going to go ahead and move my factors over. So I have 2x plus 5 and x minus 2. That was my original numerator. For my denominator, you don't necessarily have to use the box because your coefficient is a 1. I can just find two numbers that multiply to 36 and add to 13. That is going to be 9 and 4. So I have x plus 9 and x plus 4. Now, if you want to use the box for the factoring, that's totally fine. It would still give you the same answer. Now, one thing that I notice is that this right here is a division problem. Now, when I have a division problem, what I'm going to do is I'm going to change it to a multiplication problem. So I'm going to go ahead and change this to multiplication. But when I do that, I need to flip this fraction over. So the x squared minus 4 is now on the bottom, and 3x squared plus 12x is now on the top. Now, my second fraction that I just wrote in pink still needs to be factored, but I didn't want to combine a bunch of steps together, just in case you got lost. So I'm going to take baby steps, one piece at a time. Let's see, so x plus 4 times, in my numerator, 3x squared plus 12x. This right here, I need to factor out the GCF. So the biggest thing they have in common is a 3x, and when I take out a 3x from 3x squared, that leaves me with x. And I can also ask myself what times 3x gives me 12x, and that's 4. On the bottom, it's a difference of squares, so that becomes x plus 2 and x minus 2. Now comes my favorite part of these types of questions, is canceling stuff out. So I can cancel out whatever's the same on top that's also the same on the bottom. So I can cancel out these x minus 2's, I can cancel out x plus 4, and that's it. Whatever you're left over with is going to be your solution. So I have 3x, 2x plus 5, over x plus 9, and x plus 2. And that cannot be simplified any further. So there is my final answer. And that takes care of operations with rational expressions. All right, next up, inverses of rational expressions. These are actually my favorite types of problems. So when I'm finding the inverse, what I want to do is I want to switch my x's and y's. So originally I have y equals 3x minus 4 over 7x. Now, since I want to find the inverse, I'm going to switch my x's and y's. So instead of y equals, I have x equals 3y minus 4 over 7y. Now, right now, I have a fraction, so I need to get rid of that fraction, and the way that you do that is to cross multiply. So I'm going to multiply x and 7y. That gives me 7xy equals 3y minus 4. Now what you need to do is you need to get your y's on the same side, because what we're trying to do is we are trying to solve for y, and in order to do that, I need my y's on the same side. I'm going to go ahead and subtract 3y from both sides. And when I do that, I can just rewrite it. So I have 7xy minus 3y equals negative 4. I'm going to go ahead and move this over here because I don't want to run out of space. I'm just going to rewrite it. 7xy minus 3y equals negative 4. Now, one thing I notice, both of these have a y in common. So I'm going to go ahead and factor out that y. When I do factor out that y, that leaves me with 7x minus 3. And right now, y is being multiplied by 7x minus 3. So to undo that, I'm going to divide both sides by 7x minus 3. And now I can write my final answer as the inverse. C inverse of x equals negative 4 over 7x minus 3. So a lot of algebraic skills come into play when you're finding the inverse of rational functions. Let's do another one. Again, I'm going to start by switching my x's and y's. So instead of y equals, I'm going to write x equals 5y over 2y plus 3. Now for this denominator, I'm going to put it in parentheses because this is actually two terms being added together. So I want to make sure that they stay together, especially when I do this step right here of cross multiplication. So I have x times 2y plus 3 equals 5y. Now, anytime I see something in front of a parentheses, my instinct is to distribute it. So that's exactly what I'm going to do. I'm going to distribute x into the parentheses. That leaves me with 2xy plus 3x equals 5y. Now from here, it's just like with the last problem where I need to get my y's on the same side. I'm actually not going to touch this y because it's already by itself. So I'm going to go ahead and move this y to the other side. And to do that, I'm going to subtract 2xy from both sides. So that leaves me with 3x equals 5y minus 2xy. And just like the last one, I'm going to go ahead and rewrite it. But just like the last one, I'm going to have to factor out that y because right now when I have y in two separate terms, I can't really solve for y. But if I factor it out, that gives me y times something, which in this case is 5 minus 2x. And then to get my y by itself, I can divide. So I'm going to divide both sides by 5 minus 2x. And then my inverse notation, so d inverse of x equals 3x over 5 minus 2x. Now, you could get a different answer for this, and that all depends on what you choose to do at this step right here that I'm currently circling. If you choose to move this 5y instead, it still would work out. You would end up having to move this 3x as well. You'll just have a different answer with different signs. So another possible answer, if you took the other route, would be negative 3x over 2x minus 5. And both of these answers are correct. But again, it just depends on your thought process and what you end up doing right here. All right, so that takes care of inverses of rational functions. Next up, reciprocals. So reciprocals, what you need to remember is essentially you can never divide by 0. So what ends up happening is I'm going to go ahead and pinpoint all of my x-intercepts. My x-intercepts are when they cross the x-axis. Now, my y value at these points are 0. And unfortunately, you cannot divide by 0. So the reciprocal is flipping a number over. So for example, if I had the number 4, its reciprocal is 1/4. If I have the number 1/3, its reciprocal is 3. So when I have the number 0 and I take the reciprocal, it's 1/0, which you can't have. So anytime you do have these x-intercepts, what's going to happen with your reciprocal function is it's going to become a vertical asymptote. So at each one of these points, I'm going to go ahead and graph a vertical asymptote. Same thing with this graph over here. Got my vertical asymptotes. This one has a lot of vertical asymptotes, but that's okay. We're just going to go with it. And each one of these reciprocal functions also has a horizontal asymptote, and that's always going to be your x-axis. So don't forget to highlight your horizontal asymptote as well, because that's going to help us with our graph. Now, in order to get the rest of the graph, we have to remember what a reciprocal is. So for example, if I look at this y value right here, this y value right here is 1, 2, 3, 4, 5, 6. So my y value is 6. So when I take the reciprocal, that is 1/6. So that gives me a number very close to 0. So I'm going to plot my point over here. Now you can pick any point on your graph. So for example, if I pick 1, where my y value is 1, well, the reciprocal of 1 is just 1. So I'm going to graph a few points. That way I can figure out what my sketch is going to look like. And here is the first piece of my reciprocal graph. For the one in the middle, I'm going to look for my y values of 1, because the reciprocal of 1 is 1. And then you can also look for 2's. The reciprocal of 2 is 1/2. So here is my y value of 2. Its reciprocal is 1/2. So I'm going to go ahead and plot the point 1/2. And then I can already see what my shape is going to be. So I can go ahead and connect these two pieces and then extend towards the asymptotes. Same thing for my other piece. I'm going to look for my 1's, and then my 2's are at 1/2. So y coordinate of 2 would create a reciprocal of 1/2, and then I can go ahead and sketch the rest of my curve. Okay, and then for this last piece over here, I have 1, 2 is at 1/2. So there's my last piece. Now, one thing I want you to notice is the only time I had a reciprocal graph, so not green, that's definitely purple, the purple pieces are wherever the red graph existed. So what I mean by that is I don't have any purple pieces over here. I don't have any purple pieces over here. Don't have any purple pieces over here. And don't have any purple pieces over here. And that's because my original function, the red graph, was not in any of those areas. So if it helps you, you might want to color out the pieces that have no original graph. That way, you're not sketching the reciprocal where there shouldn't be a piece. So going to my next graph, again, which I'm going to do in purple, I'm going to start with this first red piece. Let's see, 1 is over here, 1/2 is pretty close to right here. It's very, very close to the asymptote, which is okay, but it's going to extend towards your horizontal asymptote. For the next piece, I look for my 1's. Let's see, this vertex piece right here is at 1, 2, 3, so 1/3, be about right there. And then I can go ahead and extend towards my asymptotes. This other piece, let's see, got 1 right here, 1 right here, and I'm going to go ahead and just connect towards my asymptotes. And then over here, this is pretty close to 1. So I'm going to go ahead and plot my point at 1, extend towards my asymptotes. And then my last piece, I've got my 1, 2, my y value of 2, which is right here. That's going to create a 1/2 for the reciprocal. So about right here. And again, I can sketch towards my asymptotes. So really your graphs for these look like a bunch of U's and L's. So just make sure, again, you're not graphing where the original graph did not exist. So technically, I should have colored this piece as well. There we go. All right. That's it for graphs of reciprocal functions. Next up, holes and asymptotes. So holes and asymptotes come from a lot of factoring once again. So again, if you're good at factoring, these should be easy peasy. If you struggle with factoring, pay extra close attention. So up top, I do not need to use the box because my coefficient is just a 1. So I need to find two numbers that multiply to -35 and add to -2. That is going to be -7 and positive 5. On the bottom, I'm going to go ahead and multiply using the box because I see my leading coefficient is a 2, so that's 30. Two numbers that multiply to 30 and add to 13 are 10 and 3. I'm going to go ahead and set up my box over here. So I've got my 2x squared, 15 over here, 10x, and 3x. Going to pull out the GCF, start with my columns. This one has an x in common. This one has a 5 in common. My row has a 2x in common and a 3 in common. So my factors are 2x plus 3 and x plus 5. Now I am going to simplify, so I notice my x plus 5s are going to cancel out. And anytime I have factors that cancel, that is going to leave me with a whole. So since x plus 5 was the factor that canceled, I'm going to set it equal to 0, and I'm going to solve for what that is. And that's going to give me the x-coordinate of the whole. So the whole is an actual point, so you need both an x and a y-coordinate. Now for the y-coordinate, I'm going to focus on my leftover function. And I'm going to take negative 5 and plug it into my leftovers. So up top, that gives me negative 12. On the bottom, that gives me negative 7. So that reduces to a positive 12/7. Your vertical asymptote comes from any factors that were left in the denominator. So my factor that was left in the denominator was 2x plus 3, and I'm going to set that equal to 0. Subtract 3 from both sides, I get 2x equals negative 3. Divide by 2, and you get x equals negative 3/2. So that's going to be your vertical asymptote. So again, wholes come from factors that cancel. Vertical asymptotes come from leftover factors in your denominator. Now for the horizontal asymptote, we can look at our dominant terms. So right here, my highest exponent is going to be 1x squared. On the bottom, it's going to be 2x squared. Since my dominant terms are in both the numerator and the denominator, my horizontal asymptote is going to be a ratio of those leading coefficients. So that's going to be y equals 1 over 2. All right, let's do another one. I'm going to go ahead and start by factoring. Up top, I don't have to use the box. I can just find two numbers that multiply to 12 and add to 7. That's 3 and 4 over 4x minus 1. Now, if you look at this function, there is absolutely nothing that cancels out. So since there is nothing that cancels out, that means we don't have any wholes. Your vertical asymptote comes from your denominator. So I'm going to go ahead and find the 0 of my denominator. So I'm going to set it equal to 0, add 1, divide by 4. So I get x equals 1/4. Now for my horizontal asymptote, again, I'm going to go ahead and look at my dominant term. So my dominant term in my numerator is x squared, and that is higher of a degree than what I have in my denominator. So that means this does not have a horizontal asymptote. So that is none. Now, if you ever forget, you could actually graph this. And if you do graph it, and this is a very generic graph, it's going to look something like this, where you do not have a horizontal asymptote, you have a slant asymptote. Now, this was just a sketch. It's not the actual graph of that. It's just an idea of what the graph would look like. So there's no horizontal asymptote. All right, last one. Again, I'm going to start by factoring. So this becomes x plus 3, x minus 3 over x minus 3. And I notice my x minus 3s are going to cancel, which is going to leave me with a whole. So I'm going to go ahead and set the factor that does cancel equal to 0, and I get x equals 3. So that means the x-coordinate of the whole is 3. For the y-coordinate, I need to look at my leftover function. leftover function is x plus 3. So now I'm going to take my x coordinate and plug it in. So now I have 3 plus 3, which is 6. So y coordinate of the whole is 3, 6. Now for this one, I do not have any factors left over in the denominator, so I do not have a vertical asymptote. Also, for my horizontal asymptote, if I look at my dominant term, it is in my numerator. Dominant term in the numerator means I do not have a horizontal asymptote. And also, if you were to graph this right here is a linear function. Linear functions do not have asymptotes. So your graph would look something like this, just a straight line, no asymptotes. Now, one scenario that you did not have was when we had a horizontal asymptote of y equals 0. So let me give you an example of that. That would be something like f of x equals x plus 3 over x squared minus 9. And this one, my dominant term is in the denominator. So when your dominant term is in the denominator, your horizontal asymptote for this one would be y equals 0. So just another example since there wasn't one like this on your test review. All right, limits. Okay, so a couple different types of limits here. If you see this plus over here, that means I am approaching my x of 4 from the right-hand side. So here's my x of 4. I'm going to travel to my x of 4 from the right-hand side. And I want to find the corresponding y coordinate that I'm heading towards, and that is -2. So there's your answer for that one. Now I want to do the same thing, except I'm approaching 4 from the left. That's what that negative means. So I'm going to travel along my graph as I approach my x of 4, and I want to see where that y coordinate is heading towards. And this one is -3. Now, if I look at this limit, it's just saying as x approaches 4. There's no plus or minus next to it, so that's not the right or the left hand. It's just finding the limit at 4. Now, since my left hand and my right hand limits were not the same, that means the limit as x approaches 4 does not exist. If, say, both of these were like -3 and -3, then the limit would also be -3. So in order for the limit to exist at a particular x value, its left hand and right hand limits have to be going towards the same thing. I'm going to go ahead and erase this so I can use the rest of my graph. Okay, so let's look at the limit as x approaches -infinity. So let's look for when x is -infinity. -infinity is over here. Where's my graph going towards? My graph is just going to keep going down. And which y value is it going down towards? Y value is also -infinity. All right. You're always looking for y values when you are finding the value of a limit. Just keep that in mind. Okay, so find the limit as x approaches -1. So here's -1. So I'm going to approach my x value of -1 from the left and the right hand side. So when I come at it from the right hand side, my y value is approaching 2. When I come at it from the left hand side, my y value is also approaching 2. So that means the limit as x approaches -1 is 2. Even if it's an open circle, the limit still can approach a value that's in an open circle. Now notice what letter F is asking for. Now letter F is asking for the actual y value when x is -1. So this is saying find j of -1. So when I look at -1, the actual y value is this closed circle, and that's at +1. So this answer is going to be +1. All right, last piece. For these limits, we can look at dominant terms. So if I look at my first one, the limit as x approaches -infinity, 2 over x minus 1 plus 6, my dominant term is down here at the bottom of my fraction. So that means the limit as x approaches -infinity of just this piece is going to equal 0. So the limit of this is 0. since my dominant term's on the bottom, and 0 plus 6 is 6. So the limit for that entire thing is going to be 6. For letter B, I'm going to look for my dominant term again. So my dominant term is the one that approaches infinity the fastest. Your exponential functions will always approach the fastest. If you do not have an exponential function, then you start to look at just the exponents, which I'll get to once we get to some of the other problems. Now right here, if I were to plug in, so now I can just focus on the limit as x approaches infinity of just my dominant term. Okay, the other pieces don't matter because the dominant term really just wipes out the other pieces. So if I were to take a really, really large number, take negative 2 to the x and plug in like a really, really, really big number, what you're going to get is you're going to get a really, really big negative number. And that negative number is going to be approaching negative infinity. So the limit for this one is approaching negative infinity. Okay. Now for this one, if I look at my dominant terms, my highest exponent up top is a cube. On the bottom, also a cube. So again, I'm just going to look at the limits of these two pieces. So I have 8x cubed over 6x cubed. Well, if I were to reduce this, my x cubes are going to cancel. So I have the limit as x approaches infinity of 8/6. Well, the value of 8/6 doesn't change based off of what x is. So that means this limit is going to be 8/6, but of course we want to reduce it. So it is 4/3. So the limit for this is 4/3. This goes back to when my dominant terms are on the both top and the bottom, your limit is going to approach those leading coefficients. All right, letter D, let's look for my dominant term. Dominant term has the highest exponent, and my highest exponent is on the top. So if I were to take a really large number and plug it into 9x to the 4th, that is going to also give me a very, very, very large number. So that means the limit is heading towards infinity. I'm going to go ahead and skip letter E for a second. I'm going to jump to letter F since I'm still talking about dominant terms. For this one, my dominant term is on the bottom. So that means if I were to take a really, really large number and put it on the bottom of a fraction, that's going to head towards 0. It's going to get very, very small. So that means this limit is going towards 0. So just to summarize, if the dominant term is on the top of the fraction, that limit is infinity. That's this case over here. Dominant term on the top heads towards infinity. If your dominant term is on the bottom, that's this one over here, that limit is going to head towards 0. If your dominant terms are on the top and the bottom of your fraction, that's this example over here, that's going to be your leading coefficients. So 8/6, which we reduce to 4/3. All right. If it's not a rational function, so that's this right here, look for your dominant term and just see where that dominant term is heading towards. So negative 2 to the x, if I were to plug in a really, really large number, that would head towards negative infinity. All right, this last one is asking for the limit as x approaches 4. So now I actually have a numerical value. So what I want to do is I want to plug in that numerical value and see where it takes me. So I'm going to plug in 4. So I have 12 minus 2, which is 10, over 4 minus 2, which is 2. And of course, 10 over 2 is just 5. So that means this limit is heading towards 5. So this one actually had a number to plug in, so I went ahead and plugged in the numbers. For the other ones, I was looking at really, really large numbers because you're looking at infinity or negative infinity. So you can go ahead and either plug in really, really large numbers, or you can look at dominant terms, or you can even look at the graph and see what the graph is doing. All right, so that covers all of the problems from your Chapter 2 test review. Don't forget to practice, okay? You need to practice these problems over and over and over again until you can do them successfully. All right, good luck on your test.